Good afternoon, everyone. Thank you for your invitation. Let me firstly introduce myself. I'm Rawane Ramadan, a PhD scholar and teacher assistant at Beirut Arab University, Lebanon. Today, I will present a glimpse of my PhD thesis about the incorporation of biofiber on the volume change of cement paste. I will walk you through my presentation. I will start by introduction, aim and objectives, literature review, experimental program, results and discussions, and finally, conclusion. Concrete is the most used building material. However, concrete is weak in tension and is prone to cracks. Shrinkage in concrete is a crucial challenge. It can arise from various factors such as cement type, water to cement ratio, and the changes in temperature and humidity. So aiming for sustainability, especially in the field of construction material, has urged the usage of renewable resources like natural fiber, since cement in concrete is responsible for around 4 to 8% CO2 emission. The addition of biofiber to concrete promotes a sustainable building at low cost. So our aim is to clarify the incorporation of based plant natural fiber on the internal and external volume change of cement paste. The objectives are chemical shrinkage, drying shrinkage, autogenous shrinkage, and finally expansion. Moving to literature review, what is chemical shrinkage? Chemical shrinkage is the internal volume change due to the hydration of cementitious materials. After the hydration product's volume is lower than the volume of cement plus volume of water. Le Chatelier contraction exhibited that total chemical shrinkage for normal Portland cement was about 4.6% by cement weight. Three main measurements for chemical shrinkage: gravimetry, which tested the external volume change of cement paste, dialectometry, and piconometry. Among these measurements, the dialectometry is the most used technique. What is drying shrinkage? Drying shrinkage is the loss of moisture in concrete. It is controlled by using concrete with lower water-cement ratio or by adding some materials leads to its reduction. What is autogenous shrinkage? Autogenous shrinkage is the change in concrete volume due to the chemical reaction between cement and water. It is actually the microscopic reduction in the external dimensions of cement particles during curing without any loss of moisture. It can be either expansive or contracted. Total chemical shrinkage mechanism. After the hydration of cement and water, the chemical shrinkage occurs in the initial setting time, and the autogenous shrinkage, which is represented here, the external volume change, is equal to the chemical shrinkage. After the setting time, the voids are generated due to the hydration, indicating the internal volume change. The accumulated voids plus the autogenous shrinkage represent the total chemical shrinkage. Some studies about the incorporation of natural fiber in concrete. In previous research, roseal, sisal, coconut, hemp, and jute fiber have been found to increase the mechanical properties of concrete. Atay stated that samples containing washed rice straw fiber had lower drying shrinkage. Falho et al. Found that sisal fibers reduce plastic shrinkage and restrained shrinkage cracking. Ghanem et al. Found that capillary water absorption coefficient and total water absorption increase with the increase of palm fibers. The scientific name of the plant used in our study is Phragmites-Australis. This plant is tall and can grow to a height more than 4.6 meters. The other specifications are illustrated here. This plant can be found on every continent except Antarctica, and it is widely available in Lebanon, especially in Bekaa along the Litani River. This plant is invasive and grows fastly and causes problem to farms, so they usually burn it. So in order to save our environment, it is more beneficial to use the stems of this plant in concrete purposes. So this plant, it is a multi-purpose grass, and usually for construction purposes, we use the stems. The following are the steps how to obtain Phragmites fiber. So first of all, the plants are collected and the stems are sun-dried, then cut through cutter machine to a different lengths. These stems are then treated with NaOH solution, and the final step is to wash and very dry weld these fibers to be added to the mix. Experimental program. The cement used is PAL 42.5, and the Phragmites-Australis have Phragmites-Australis fibers have a 1 centimeter long and 2 millimeter wide, and had a density of 665 kilogram per meter cube. Also, the tensile strength of PA stems is done at the AU laboratory, and the stress strain curve is plotted here. This table presents the mixed proportion. Here, the addition of PA fibers are 0%, 0.5%, 1%, and 2%, and the water to cement ratio was kept constant at 0.55. Test procedures. Chemical shrinkage test is tested according to ASTM C1608. The steps are, first of all, the cement and PA fibers are dry mixed for a few minutes, then poured into a 250 milliliter glass bottle to a thickness of 2 centimeters. The third step is to add the water to the top of the bottle. A 2 milliliter graduated pipette is inserted through a hole in a rubber stopper, and the final step is to add a drop of oil to prevent the evaporation of water. Drying shrinkage, autogenous shrinkage, and expansion were tested according to ASTM C490. The tests were conducted on prisms on size 25 by 25 by 2085 millimeters. The tests were performed using a dial gauge. Moving to results and discussions, all shrinkage parameters data are collected at 7 days. As shown here in this plot, the chemical shrinkage decreases as PA fiber increases. This decrease is mainly due to the fact that PA fiber have chemical components which may delay the hydration process. Same trend here was shown for drying shrinkage. Also, drying shrinkage decreases as PA fiber increases, and here the percentage decrease achieved a value of 30% when 2% PA fiber was added. This is mainly elucidated by the fact that the chemical treatment reinforces the thermoplasticity of PA fiber and increase the surface toughness and achieve a strong bonding between matrix and fibers. Moving to autogenous shrinkage, also autogenous shrinkage decreases as PA fiber increases. Here, the reason for this decrease is mainly due to the fact that PA fiber could stock some moisture during mixing and release this moisture later on to the cement paste over time. Expansion also decreases as PA fiber increases, and here the percentage decreases is more than the other shrinkage parameters, about 50%. Here, the reason for this decrease is that the PA fiber restricts the expansion of bars during curing. Relation between length change. This plot presents the relation between chemical shrinkage and shrinkage parameters such as drying shrinkage, autogenous shrinkage, and expansion. The correlation between chemical shrinkage and autogenous shrinkage is positive, and this is due to the fact that in initial setting time, the autogenous shrinkage represent the external volume change, which is equal to the chemical shrinkage, and it is equal up to 8 hours. Then, as pozzolanic reaction increase, the chemical shrinkage continue to increase. For also chemical shrinkage and the drying shrinkage, there is a positive correlation, and this is due to the fact that chemical shrinkage is a driving force for drying shrinkage that occurs in the hardened stage. However, there is a negative correlation between chemical shrinkage and expansion, and this is due to the fact that the pores in water expand whereas no exist of shrinkage, so that there is a negative correlation between expansion and chemical shrinkage. As a conclusion, PA fibers have a crucial role in controlling shrinkage. Chemical shrinkage decreases with an increase in PA fibers, about 2.22% when 2% PA fiber was added. Drying shrinkage, autogenous shrinkage, and expansion decreases by 30%, 25%, and 55% respectively, when also 2% PA fibers was added. We have a positive correlation between chemical shrinkage and drying shrinkage, and chemical shrinkage and autogenous shrinkage, and however, there is a negative correlation between chemical shrinkage and expansion. Thank you for your attention. Any question?